Hello, welcome back to our mini course on Discrete Calculus with the Wolfram Language. I'm Alistair Forsyth, and this video will be going over the Fibonacci sequence. The Fibonacci sequence is classically defined by the recurrence relation f sub n is equal to f sub n minus 1 plus f sub n minus 2 for integers n greater than or equal to 2. We typically define f sub 0 equal to 0 and f sub 1 equal to 1. This generates the sequence 0, 1, 1, 2, 3, 5, 8, 13, and so on and so forth. Different resources sometimes leave the 0 out, but I prefer to leave it in. And also they sometimes define the sequence a little differently, but I prefer the recursive definition. This lesson will go over many things big and small related to this sequence in particular. Starting out with some related concepts, we have one that you probably heard of from popular media. The golden ratio, often denoted phi, is an irrational number, 1 plus the square root of 5 divided by 2, or roughly 1.618. Now this is related to the Fibonacci numbers because the quotients of consecutive Fibonacci numbers actually converge to the golden ratio. We can confirm this in the Wolfram language using the discrete asymptotic function. And we can see that Fibonacci of n divided by Fibonacci of n minus 1, as n grows without bounds, is equal to the golden ratio. Along with that, we have Negafibonacci numbers, which are created by applying the recursive definition of the Fibonacci sequence backwards. You see, they kind of function as like the negative indices of the Fibonacci sequence. Something that's cool about them is that any integer can be uniquely represented as a sum of Negafibonacci numbers using no two consecutive entries. The exception to this is that all codes written in this manner end with 11. Along with that, we have Fibonacci polynomials, which are polynomials written out in the form f sub 0 of x is equal to 0, f sub 1 of x is equal to 1, and then for every other n, f sub n of x is equal to x f sub n minus 1 of x plus f sub n minus 2 of x. Now in the Wolfram language, Fibonacci of n comma x generates f sub n of x. And these can kind of be thought of as a generalization of the Fibonacci sequence with f sub n equal to f sub n of 1. Here we have a piece of code that generates the first 6 Fibonacci polynomials from n from 0 to 6. And now these come out to be 0, 1, x, 1 plus x squared, 2x plus x cubed, 1 plus 3x squared plus x to the 4th, 3x plus 4x cubed plus x to the 5th, and so on and so forth. Another related concept we have are Lucas sequences. You see, Fibonacci numbers are actually a special type of Lucas sequence. Lucas sequences themselves are just constantly recursive sequences defined by Lucas sub n of p comma q is equal to p x sub n minus 1 minus q x sub n minus 2. Now these can be written with either a u or a v, and they just change the starting values of the sequence. For example, u sub 0 of p comma q is equal to 0, and u sub 1 of p comma q is equal to 1. But for v sub 0 of p comma q is equal to 2, whereas v sub 1 of p comma q is equal to p. Using this, we can generate Fibonacci numbers from u sub n of 1 comma negative 1, and the Fibonacci polynomials from u sub n of x comma negative 1. Along with that, we have Lucas numbers, which are kind of a base kind of Lucas sequence similar to the Fibonacci numbers. The Lucas numbers themselves are generated from v sub n of 1 comma negative 1. Similarly to Fibonacci polynomials, Lucas polynomials are generated by v sub n of x comma negative 1. In the Wolfram language, Lucas L of n comma x generates v sub n of x comma negative 1, with x equals 1 being the nth Lucas number. We can write this out in a nice little table of the first 6 Lucas polynomials. This comes out to be 2x, 2 plus x squared, 3x plus x cubed, 2 plus 4x squared plus x to the 4th, 5x plus 5x cubed plus x to the 5th, and then 2 plus 9x squared plus 6x to the 4th plus x to the 6th. Along with that, a neat little function of the Wolfram language is if we take rsolve and then we enter in the recurrence relationship that defines the Fibonacci numbers, it'll actually give us a combination of the Lucas numbers and the Fibonacci numbers. It does this because any sequence that follows that recurrence relation can actually be written out as a combination of those two sequences. Moving on, we can look at some notable properties of the Fibonacci sequence. To start with, the number of digits in f sub n is actually asymptotic to n log of base 10 of phi. Along with that, f sub n itself is actually asymptotic to phi to the power of n over the square root of 5. And we can actually show that within the Wolfram language using its discrete asymptotic function, which comes out to be the golden ratio to the power of n over the square root of 5, which is copacetic with what we thought. Along with that, we have Carmicheal's theorem, which states that every nth Fibonacci number has a new prime factor not shared by the earlier indices, with the exceptions of 1, 8, and 144. And this was all proven back in 1913. When examining f sub n mod m, we can see a certain relationship start to form. The resulting sequence will be periodic, and will actually have a period of no more than 6m. The exact period it has is called a Pisano period, or pi of m. Currently, an exact function for pi of m is not known, but some values are known. A couple of those values are 1, 3, 8, 6, 20, 24, 16, 12, 24, 60, 10, and then 24 again, and so on and so forth. Moving on, we can look at some notable applications of the Fibonacci sequence. Most notably, the number phi is actually found all over the place in nature. For example, the number of petals on a flower is often a Fibonacci number ranging from f sub 4 to f sub 10. Along with that, snail shells, nautilus shells, and even the cochlea of our inner ear tend to follow the golden spiral. And the golden spiral is just a logarithmic spiral with a growth factor of phi. We can actually map that out in the Wolfram language using its polar plot function and a growth rate of phi. Now, if I'm being honest with you, I think some popular media outlets have overblown how much the golden ratio is found in nature, but it is kind of cool to see it sometimes. Along with that, the nth Fibonacci number can actually be interpreted as the number of ways you can describe n minus 1 using only combinations of 1 and 2. For example, the fifth Fibonacci number is the number of ways you can describe 4 using only 1 and 2, which gives us 1111, comma, 112, comma, 121, comma, 211, comma, 22. This should tell us that the fifth Fibonacci number should come out to be 5, and we can confirm that using the Wolfram language. Along with that, the nth Fibonacci number can also be interpreted as the sum of the shallow diagonals on Pascal's triangle, and we can demonstrate that using this nice little picture that I grabbed from Wolfram Math World. It can be interpreted as the number of ways 2 by 1 dominoes could be used to cover a 2 by n minus 1 checkerboard. To demonstrate that, we also have another picture from Wolfram Math World with a value of n equals 5. And along with that, out of all things, the probability of not getting 2 heads in a row in n tosses can be written as f sub n plus 2 over 2 to the power of n. I thought that one in particular was kind of funny because it's so unintuitive to me, you know. Anyway, today we went over the Fibonacci sequence and Fibonacci polynomials. We looked at Lucas polynomials and the Lucas sequences, and we look at some of their notable properties and applications. For further details, you can check out the reference page for the Fibonacci numbers, and in the next video we'll go over some more tools for manipulating sequences, namely permutations and combinations. Again, I'm Alistair Forsyth, and thank you for watching. Bye-bye.